Hello, I'm Thomas Steffen and this is my video about a paper presented at the SAE World Congress Experience 2023 in Detroit. The paper is called Moments of Power, a statistical analysis of drive cycles and powertrains. And it presents a new idea or a new way of thinking about how to analyze the energy consumption of a vehicle. This paper brings together three topics and then makes it a little bit more complicated than the average paper. It talks about drive cycles, it talks about the statistical properties of these drive cycles, and it talks about how these properties interact with the powertrain model. So let's start with the drive cycles because that's the easy bit. Drive cycles have been used for a long time in automotive engineering. And they serve a purpose because they kind of represent how vehicles are being used. Some cycles do this very well. So the FTP 75 from 1975 perfectly captures the relaxed suburban driving style that is common in large parts of America in an automatic transmission vehicle. On the other hand, we have cycles that are maybe less representative, and the EUDC test cycle is very well known for hitting certain speed points, but for not really representing the variability and the acceleration in common driving. So although it has been used for a long time, we know that the EUDC is a poor cycle. It does not give you results that are comparable to real-world economy figures. But we don't know exactly why. We do have a better cycle, of course. The World Harmonized Light Duty Test Protocol, WLTP, has a cycle 3A, which represents modern driving styles much better. It has faster speeds, a more aggressive driving style. It can differentiate by vehicle classes, and it was meant to be a globally harmonizing cycle. It is better than other cycles that we have, but it is still not perfect, and it's still not an exact representation of what people actually do. So, how do these cycles differ? We have looked at this question many times, and we see, for example, that they have different speed ranges. I've got three cycles here, the FTP 75, the NEDC, so the European driving cycle, and a research cycle, the Artemis set of cycles. And the first thing you can see is that the speed range is different. The Artemis cycle goes up to 150 kilometers an hour, or 42 meters per second, 93 miles per hour, which represents some kind of driving that happen on European highways, whereas other cycles might have a much more limited speed range. And these histograms are definitely useful because they give us an idea of what the cycle represents. But of course, at the same time, the histogram, A, it's not really a number. We can't really easily compare one to the other, and B, it doesn't include the acceleration that is inherent in the cycle. So we want to find a way of analyzing drive cycles in an objective way. And what I'm proposing here is that we use the moments of the cycle or the moments of the distribution of the cycle. Moments are defined of the average of the power of the variable that you're looking at. And in this case, we're looking at the speed. So you take the power of the speed and then calculate the average by integrating and dividing by the amount of time. You can see that here. So we take the power, we take then the integral, we divide by the total time. And that is what is called a raw moment. You can also define central moments where you remove the average, and there are more sophisticated definitions that will come later. And I mentioned in the paper. And let's see how this works. There are four moments that are named and well known in terms of significance. The first raw moment is the arithmetic mean, so the average of the speed. Obviously, that is an important property. The second moment is the square of the standard deviation, and so that is an expression of the variation of the speed. But there are higher order moments, and the third moment is called skewness. It gives us an indication of whether the distribution is skewed to the left or skewed to the right, so how symmetric it is. And the fourth moment is called kurtosis. It gives us an impression of how long the tails of the distribution are. And of course, there are further moments, but they don't have any names. They are basically a little bit obscure and rarely used. And we'll see how these moments are going to be relevant depending on the model that we choose. So here is a view of what these moments mean. So if we have a different first moment, that just means the average of the distribution shifts to the left or to the right. That is quite simple. If we have a different standard deviation, that means the distribution is narrower or wider. And we know those two moments quite well. The skewness is a first one that is maybe not quite so familiar, and you can see it makes the distribution non-symmetric. It's a measure of non-symmetric distributions, distributions that extend to one side but not to the other side. And finally, we have the kurtosis, and you can see here it's not about the peak, it is about the relationship between the shoulders of the distribution and the tails of the distribution. And you can see the kurtosis is always in the range around 3. So a normal standard distribution would have the values mean 0, standard deviation 1, skewness 0, and kurtosis 3. So with this, let's move on to our third topic, which is the powertrain models. We need some way of modeling our vehicle so that it is open to analysis. And what we're going to use here is we're going to use polynomial models. Polynomial models are created by adding different monomials with their coefficients. And you can see the monomials plotted here on the right. So you have a constant function, a linear function, a square function, a cubic function, and so on. And from these monomials, you create your polynomial model. This has been done in automotive applications for, again, many decades, because polynomial functions are very easy to work with. They are simple and they are smooth, and they give you an approximation over the whole operating range. One of the issues with this is that they don't have any locality. So we also use models that have locality. This means if you modify any of your components here, any of your coefficients, it affects the model over the whole range. And sometimes you want a model that has more locality, where you can just tune specific areas of your model. So these polynomial models have no locality. Otherwise, they are a very good choice for basis functions. Sometimes you hear about Legendre polynomials because they have this orthogonality feature, but we don't have to go that deep into the theory here. So why do we use polynomial models? To be honest, because we've always done it, and because it comes out of the first principle model of our vehicle. If you look at a vehicle model here, that gives you a rolling resistance that is a constant force, and it gives you an aerodynamic drag, which is the square proportional to the square of the speed. You end up with a polynomial model, and we can see that here, 3 polynomial coefficients up to the square of the speed. Plus there is this acceleration term am. So according to Newton's second law, we get this term for accelerations. And this is the standard model that we have used for the tractive effort for many decades. From this, you can calculate the tractive power P by multiplying with the speed, and again you end up with the polynomial, and this is now a third order polynomial. The second model we need is a model about the powertrain. So here we are looking at an electric powertrain because these are really easy to model. A little bit easier than an internal combustion engine. And one of the simplest models that captures the behavior quite well is looking at the power consumption of the electric powertrain. It obviously depends on the tractive power, so this linear term here is the most significant term, but we also have some losses in this powertrain, and these can easily model as some constant losses. They're just idling losses or losses to keep the inverter running and keep the vehicle electrics running. and we have a square loss term. Those are resistive losses in the windings and in the wires of the vehicle. And they are square because they increase with the square of the current, which relates to the torque and therefore the power delivered. And we have fitted this model here, and you can see we have on the one axis we have the demand, that is the mechanical power. On the y-axis we have the primary power, which is the electrical power that has to be supplied, and you can see the square behavior. So for wide ranges, these curves are virtually indistinguishable from the diagonals. So basically input and output power are very, very similar. But as we move to higher power settings, we can see that this square loss does add a little bit of a discrepancy between the input and the output power, and that accounts for the loss in the powertrain. And we call these over proportional losses, in this case square losses. So now we have a model and we have our cycles, and again, using models and cycles together is something we have done for decades. So we like to plot our speed and torque scatter plot in the contour plot of the model efficiency, for example, or of the fuel consumption, just to see where we end up. This is something that has been done on a textbook level for choosing gearing, for example, for internal combustion engine vehicles, or for giving you an idea how you can optimize your powertrain and eke that little bit more efficiency out of it by moving your points to a high efficiency point. So this usage of the scatter plot together with the vehicle model is quite common and has been used for analysis as well. And this idea is fundamental to what we want to do in this paper. We just want to go one step further than just looking at this combination of the scatter plot and the model. So here comes the innovation now. This is a novel approach for analyzing the energy consumption of the vehicle. And it starts with a very simple observation. Traditionally, we will use the model that we have just defined, and we call it Y. This is the primary power consumption of the vehicle. It is the output of these two models. That is the electrical power demand of our vehicle. And traditionally, we integrate this over time. That is something that is very easy to do in simulation by just adding an integrator. And the result of this is the primary energy consumption of our vehicle. So this is how much battery our electric vehicle has used. Or if you do the same for an internal combustion engine vehicle, this is how much fuel your vehicle has used over the simulation. But you can also write this integral in a different way. You can use the expected value, so the first moment of the primary energy, primary power, and multiply with the time. This is an equivalent representation of that integral. If you insert your model y of t here, you find that this is an integral of a summation. The summation is this polynomial model that we have created, and this has been collapsed into one large polynomial that is a polynomial of the speed and a polynomial of the acceleration of the vehicle. So this is a mathematical representation of our simulation that calculates the primary energy consumption. And now what we're doing is we notice that we have an integral and a summation here, and we can flip these around because they are not depending on each other. They both have exactly the same argument. So we flip these around, we put the summation point on the left, and the plus sign here becomes a first level operator, and the integral moves into the summation. And this calculates exactly the same value. It calculates exactly the same energy. So we now have a sum of 8 integrals. And if we look closely at these integrals, we notice that these are exactly the definition of our moments. So these integrals here represent the moments of the cycle. And we can substitute this, and we can say that actually the primary energy consumption is therefore the sum of 8 moments and coefficients that come from the vehicle model. So That means if we know the moments of our cycle, we can calculate the primary energy consumption directly by adding up these moments in a weighted fashion. And we do not have to resort to integration or simulation at all. We can just calculate it. So this was a major breakthrough for me and for us in terms of getting a simpler way of calculating the energy consumption of the vehicle. And I want to show you why this is so important, because now we can actually, expand these equations and put some coefficients to it. So we see how the model gives us exactly the form that we want. And we start by looking at the tractive power. So we first calculate the tractive power, the first moment, the average of the tractive power. And you can see the vehicle model here that we had, the drag model of the vehicle, translates into an equivalent model based on the moments of the speed profile. The second order is a little bit more complicated, so we want to calculate the second moment of the tractive power because we need that later. You have to expand the polynomial first before you turn it into this moment form, and you can see this gets a little bit messier here, but still it is something that you can do by hand. It's not something that you need a computer algebra program for, although I did validate this with a computer algebra program. So we have now the first and the second moment of the tractive power. We can stick those into our motor model, which is here. So we have a motor model that is based on the moments of the tractive power, the first and the second moment, because it was a polynomial model. And that means we can now calculate the total energy consumption over the cycle. We have the full equation there. I'm not putting it on the slide here because it's a little bit lengthy, but you will find it in the paper. And it's just an equation of those moments and the parameters of our model. So this is a slightly simpler view of this model that we have created. So I did say it is a sum of 8 terms, and you can see that sum here. So we have a summation over 7 terms, and we have the acceleration term, which sticks out a little bit. And on the left-hand side, you can see a table with the coefficients. This is how the vehicle parameters relate to these coefficients, or how you can calculate those coefficients from the vehicle parameters. And so this is a very, very simple way of calculating the energy consumption of a vehicle. You can do that directly. You just do, a few 10 operations, and you know the energy consumption of your vehicle. You can therefore then calculate the economy of your vehicle. And it's really hard to overstate how significant this is in terms of simplifying this calculation, because instead of doing a simulation, we can just take the cycle and calculate the moments, which is something that has already been done for many of these cycles. And basically you can only do it once. And then we can compare different vehicles, for example, with different models, and we can compare them by just multiplying them. So if we want to assess a number of vehicles over a number of cycles, the computational effort of doing this is now absolutely minimal. And it's not just the computational effort, it's also that we have equations for doing this now. So we can see which part of the cycle affects the fuel consumption and which part of the vehicle model has the most impact on the fuel consumption or on the consumption. It's a very, very simple result that we present here. So let's do an example. We have a numerical example based on a standard vehicle model that I like to use, and we want to see how these different factors are in relation of their significance. So here's a simulation model. So we have our standard backward simulation. We have the whole vehicle model integrated in one block here. It creates the primary energy power. We integrate it and we get our consumption. The second part of the simulation, using the moments, calculates the moments and then feeds them into our statistical equation, statistical model. And you can see within the accuracy of the integration, we get the same value here. This is a model that of the Nissan Leaf that is using vehicle data published in the literature. And so it's a standard model that I use in my research. And this shows that it works. So it shows that the whole algebraic transformations that we've done are correct, and we get the same result. If we look at the numbers, because I said we have 8 terms here, we can see these are the energies that are being used in these different terms. And this is quite interesting because they represent different physical effects. Basically, 4 of these 8 terms stick out. And I'll start with the zeros moment. So that is basically a constant power use over time. This is the idle consumption of the vehicle, and it depends on the length of the cycle. The second one is the first moment. That's basically your average speed. So this term depends on the distance of the cycle, and it relates directly to the tire friction. So the higher your tire friction, the more the distance of the cycle will impact on the overall energy consumption. Then we have the third moment here. So it's not the second moment. You might think the second moment, the standard deviation, is really important. And one of the things that this analysis shows us, that the standard deviation is not important at all. It's being calculated time and time again, but it contributes a tiny amount of energy to the overall consumption. What is important is the third moment, so the skewness. And that gives us an estimate of the aerodynamic drag and how this aerodynamic drag, takes energy to overcome. That contributes to the primary energy demand. We then have a number of higher moments up to the 6th moment, and these are interaction terms, interactions between the quadratic powertrain losses and the tractive effort. So they're quite interesting, but not exactly relevant from an engineering perspective. And then we've got the last term. The last term is the expected value of acceleration squared times speed squared. So this is a measure of the aggressiveness of how much we accelerate and decelerate. And although this electric vehicle has recuperation, every time you do that, of course, there are losses involved. And this is a consequence of the square losses in our powertrain. So the harder you accelerate and the harder you brake, the more of these losses you incur. And this term here accounts for these square powertrain losses as a result of acceleration. And you can see again, it is a sizable chunk. It is 340 watts on average, and goes into our overall primary power. So the average primary power is just under 9 kilowatt over the cycle, and from there on you can calculate the total energy demand by multiplying with the duration of the cycle. And this means we can sufficiently describe a cycle for the purpose of calculating primary energy consumption if we know the mean of the cycle, the standard deviation, which is not as important, but it features into the skewness, and the harshness of the cycle. And surprisingly, these same factors also come out if you use more complex models of your vehicle. You do end up with these 3 factors that describes a cycle from its difficulty in terms of energy consumption. This is a novel result. This is a question that has been open for many decades and has never been satisfactorily answered, because in the past we have often used correlation approaches where you correlated over different cycles and different data that you have, but we've never been able to find an analytic solution to this problem. So now we have the analytic answer to what makes one cycle harder or more difficult than another cycle, or what makes one cycle, one driver, if you want to, use more fuel or more electricity than another driver. So what can we do with this? Well, that's a tough question actually. What can't you do with this? In terms of energy consumption of a vehicle, this opens up many doors for further analysis, optimization, comparison, estimation, online use of these models. Because it is so simple, you can really do an awful lot with it. And I think we will explore these different applications in turn, so there's going to be more papers that will come on this topic. What do I want to do next based on these results? Obviously, first I want to look at higher order polynomials. This is perfectly feasible within the methodology presented here, but it will mean that we rely on computer algebra system, and the equations will not be quite as nice and tidy as they're here. We will also want to look at more variables, so speed, torque, mixed terms, acceleration, and so on. See how those interact with the methodology here. The same applies. You get longer equations, but nothing changes fundamentally. There are 2 points that are interesting, which will change fundamentally how this is applied. One question is, can we deal with dynamics, especially fast dynamics, changes in acceleration such as jerk, for example? Does that make a difference? That depends on the model that you use. And finally, how do we extend this to hybrids, and how do we do different scheduling? How do we use it in a creative way so that we can design maybe a perfect hybrid control strategy? We also want to push the boundaries, and that really means doing new things and maybe adding to this methodology. The first question is, can we add limits? For example, there is a limit to how much you can regenerate because of the battery charging limit, and maybe we need to use a truncated distribution to deal with that. It's not exactly clear how you would do that. How do you deal with discrete modes such as gears? If you have a manual gear shift or an automatic gear shift with discrete gears, then this methodology doesn't apply easily. You need to work out how this discrete distribution feeds into the continuous distributions. The question is, how do you deal with slow dynamics? So for example, your battery warming up, your after treatment system warming up, what kind of impact does that have on the overall behavior? And how do you include control? Because once you have dynamics, you want to apply control. So how do you make sure that you can capture the effect of control in this methodology? And that remains to be seen. So there's a lot more work to be done, but it is looking very promising. It's looking like a lot of these questions can be answered with very simple extensions. So that brings me to my conclusion. The use of moments of a cycle in combination with polynomial models offers us an analytic solution for the energy consumption of a vehicle. This applies both for electric and for conventional vehicles. It has been demonstrated here for an electric vehicle because it is easier, but nothing stops you from doing the same for any other powertrain. There are many applications that we expect to come out of this, and we will address these in turn. We also expect that this has a profound impact on how we look at fuel economy models in the future. So we will publish more on this subject. The paper is available on the SAE Mobilus database, and it is also on figshare and the institutional repository of Loughborough University. This video is on YouTube, and the software that has been used for this paper is available on GitHub. If you do have any further questions, please write to me. I'm Thomas Steffen at Loughborough University, and this is my email. Thank you very much for listening.